Okay, well, good morning. Looks like we'll get started and see if other people drop in. Um, I haven't graded the test yet, so that's on my docket for very soon. So once we do that, we can go through it and talk about it. But I haven't looked at it yet, so that'll be it for today. So don't forget there's to check the homework schedule. There's sort of a bunch coming up just because we're packing them together because some of these things are a little bit shorter. So I think 10.2 is due this afternoon. We're actually going to cover like 3 sections today. So it's quite a lot, but hopefully they're each individually not too long. And on things that I know you have seen at some points before, either in Math 103 or in physics or in calculus classes before. And we did start to talk about it because again, chapter 10 is on vectors stuff. So we've done the intro again on that kind of thing. But so we'll typically write it with the little, you can draw a little arrow on top, or you can make it bold or whatever you want. And so we'll typically write this, if we just do it in 3D, so we'll write it with these like pointy brackets, these vector brackets. So you can write it like that, or you can write it as AI plus BJ plus CK, and those are all the components in 3D according to these unit vectors, IJ, K. They're all perpendicular to each other. And then the idea is that you can talk about the magnitude or the length. So it's just an extension of the Pythagorean theorem that we get a squared plus b squared plus c squared. And then the key is that you can talk about things like called a unit vector. So that just means that it has magnitude or length 1. And to get that from V is you just take A and divide it by the length of V, and then you take B and divide it by that length of V, and you take C and divide it by that length of V, which after a while gets to be annoying. So you just write it as 1 over the length of V, or try to, times ABC. So that will turn a vector into whatever length it is into one that's the same direction, so it still points in the same direction, but it's only length 1, which is sometimes nice. As you maybe see from the homework and from your statics classes or whatever physics classes, that these can be force vectors. So you can add things together. We didn't really talk about it, but U plus V. Well, maybe I should say, let me try that again here. And just use slightly different notation. So if you had 2 vectors, V1 and V2, and you wanted to add or subtract them together, well, you just take the components, A1, we call them A1, A2, B1, B2, C2, C2. Then you can either just add or subtract in the first component, add or subtract in the second component, add or subtract in the third component. And so it's just component-wise addition or multiplication. And the same thing, or subtraction. If you were to multiply a vector by a number, then you literally just multiply each component by a number, by the same number. If you add things component-wise, and there's lots of ways to do this, but you could say, I want to go V1, and suppose V2 was another vector, then all I do is I just basically follow it like a force. So I push out to here, I push out to here by V2, then where do I end up? Well, hopefully that makes sense. That's just V1 plus V2. So adding is pretty easy. You just draw one and you draw the other and you're done. Negative vectors, so negative V, all that means is that it's the same vector. So this is the reverse direction. And you can talk about minus, and you probably learned all these little tricks about how you do minus, but I think the easiest thing is just to reverse the direction and then just add it back on. So the fact that V1 minus V2 can be written as V1, but then you just follow the reverse direction of V2. I swear it's a lot easier than trying to remember all these little tricks. So if I went V1 and I wanted to subtract V2, instead of following V2 in the normal direction, I follow V2 in the reverse direction. So if you think of these minuses as just reversing the direction. then you go V1 and you add that on, then that will be V1 minus V2. And yeah, there's tricks to remember this, but I think that's easier just to use the fact that subtraction is just plus the reverse. So that's a lot, like all in one slot. And so you can do plus, you can do minus, you can do times by a vector. You won't be able to do division at all. So we've lost division. But at the same time, and the two things we're going to talk about today, 10.2, you gain two different kinds of multiplication. And one of them is called the, or we use the word product, right? So this one is the dot product. And then 10.3 is a second kind of product, or second kind of multiplication called the cross product. And why you'd want to do both of these things, it's you'll just sort of explore these things like, hey, I'd like to combine these way. Oh, that's the dot product. Or vice versa. I'd like to say combine them in this way. Oh, well, that's a cross product. And the difference is the result here is a number. Or we use the fancy term in this case, a scalar. So just another fancy word meaning it's a number. And then the result here is we're going to take the cross product of two vectors, and the result is another vector. So if you do the dot product, you get a number. If you do the cross product, you do a vector. I'm doing Calc 2 right now, so it's like if you do a definite integral, you get a number. If you do an indefinite integral, you get a function. So you just have to know for the context as to which one you want. So let's just try this. So if we had, I'll be a little more careful here. So if we have, this is like A1, B1, C1, and we have another vector, which is A2, B2, C2, then maybe I'll just try to do these things together. I know they're in two separate sections in the book, but, oh, and sorry. This is technically 10.3, and this is 10.4. Get the numbers right here. The dot product of these two things is written, it looks like a product. It's, I put a dot in between them, so it kind of looks like a product. And all you do is you just component-wise multiply and then add the results together. So this is A1 times A2, B1 times B2, C1 times C2, and then I just add them together. And initially you're like, really? What does that mean? Well, we just probably have figured this out and then backed it out and said, hey, let's call that the dot product because that's pretty handy. So again, yeah, you just end up with a number when you do this. And you can notice the same thing is that if I took and I went V2 dot product V1 is the same. So you go way back in your brain, you're like, let's see if I do a product this way and then I reverse it and I get the same thing. The fancy word is that you can say that the dot product is commutative. So I can do dot products in either order and I'll get the same answer. And that's just because this is, you know, A1 times A2 and A2 times A1 for numbers is exactly the same. So if I reversed this part, it wouldn't matter. If I reverse this part, it wouldn't matter. If I reverse this part, it wouldn't matter. And I know it can add in any order. So, so good. So let's try one with some numbers in it because I get carried away with symbols too much. So if this was like 1, 0, 2, and V2 is, say, 3, 1, minus 1, then you can compute a couple of these dot products. In particular, let's see, we'll do the first one. So V1 dot V2, then all I do is I multiply the 1 and the 3, the 0 and the 1, the 2 and the minus 1, and then I just add them up. So don't use that. This would be 1 times 3 and 0 times 1 and 2 times minus 1. So you can always check my math in here. So that's 3, 0, and minus 2. So I'll end up getting 1 is the dot product there. V1 dot V1 sometimes will be usually the dot product of something with itself. So that is just going to be, use the same vectors. So that's 1 times 1, 0 times 0, 2 times 2. So just multiply, basically square them out, right? So that'll be 1 squared plus 0 squared plus 2 squared. And that's equal to 5. Now you might be like, I've recognized that before, where I just like square that one, square that one, square that one, and then take a square root. And it turns out that this is exactly the magnitude of the vector, but squared. So when you're doing the dot product, that's one of the first identities, is that V dot V in general, running out of room here, but is equal to the length squared. So the dot product is kind of like a measurement of length in some way. Certainly if you do the dot product of a vector with itself, it is exactly the length of a vector. So that's pretty cool. You can also have examples where, let's see, maybe down in 2 dimensions. You can do this in 2 or 3 dimensions. So sometimes the book uses different letters, so let's just try this. So if I said that this is 1, 2, and maybe we'll use W here, and W is, say, 4 minus 2. So if we do the dot product there, V dot W, we multiply the 1 and the 4 together. So we get 1 times 4, and then we multiply the 2's together, and we get 2 times minus 2, and we add. And you're like, wait a second, we get 4, and then we get minus 4. We add them together, and boom, we get 0. So, all right, so wait, I do it. But neither one of these is 0, right? So it's not quite like regular multiplication. You can take 2 things that are not 0 and dot product them together and get 0. Now, if we draw these out, that might give us a little hint as to what's going on. So if I drew the first vector where I go over 1 and up 2, then I get V. And if I go over 4 and down 2, I get W. The thing to recognize, that's W. The thing to recognize here is that if you were to look at this angle in between them, it turns out it's exactly a right angle. And this is a nice property, the second one that we've already derived. So not only does it somehow talk about length, but if the dot product is 0 between 2 vectors, this will only happen if the angle between them, or fancy term, right, be like this symbol. Seen that for a while. That's just the perpendicular symbol. As you say, if the dot product turns out to be 0, then they're perpendicular, and actually goes, they're the same thing. So perpendicular and dot product 0 are one of the same thing. So that's a nice thing, is it can somehow talk about not only length, but it can talk about the angle between them. So that's kind of nice. Yeah. And one more sort of key property before we start doing an application of this is, I don't do too many derivations in here, but this is not a bad one to do here, is if I look at the length of 2 vectors, of the subtraction between 2 vectors. So why would I do this? Well, again, it's sort of playing around here that if I Again, try to do this. Let's see. This is V, and suppose that this is W, and I wanted to know what the vector is V minus W in this picture. So what I do is I'll go V, and then I want to take the opposite of W. So there's that. I'll go V, and then the opposite of W is here. So again, if you think of this as V, and then I'm adding on the opposite of W. So I go V, and then I want to follow the opposite of W. I get V. Nope, that's not right. Try again. Oops, lost V. Then, so if I go V, and then I go the opposite of W, so I have to move it over here. Vectors don't have necessarily a fixed point. You can move them as long as they have the same direction and the same length. They're the same thing. So if I go V and then minus W, this is minus W. This vector is V minus W because I went V and then I followed the opposite of W. Look at this vector. But here's the other cool thing, you know, and this is probably what you learned when you did this before, is you can take vectors and you can move them around. So as long as you don't change the direction or the length, this one right here is also V minus W. And I hate to say it, but it's like, what do? You like draw them and you draw from one tip to the other tip if you're subtracting them. I never remember any of that. So I just go V and then the opposite, and then you can move these things around. So if you put in W and V and W, V minus W, you do get this triangle here. The only catch is that it's not a right angle, certainly the one that I've drawn, but at least it is some angle here. And now I'm going to pull something definitely out of the past. This is the law of cosines. And if you don't remember what that is, I'll tell you what it is. If you want to find the length of a vector or the side of a triangle that is opposite of the angle, then it turns out that it is one length of one side, so that'll be the length of V squared, so it's a length squared. The next one squared, the length of W squared. And you know, if this was a right angle, that would be it. This would be A squared, B squared, and C squared. Because if it was a right angle, this thing would be the hypotenuse. But if it's not a right angle, you have to invoke the law of cosines, which is, so let's see, law of cosines is, so you want C squared is A squared plus B squared, but then you have to subtract off 2AB times the cosine of the angle in between. So that's a blast from the past. You apply that to this triangle where C is this B minus W, that's the first part, and then A and B are the separate lengths. So I'll have the length of V times the length of W times the cosine of the angle between them. So I'm going to do this sort of quick derivation in here using dot products and to see why did I do this.
Sir,
yeah,
I'm kind of confused on how V minus W is equal to V plus W. Wouldn't you put W on the tip of V and then it would make that really really obtuse angle, or like if it was V plus W?
V plus minus W is what V minus W is. So what that means is I follow this vector V from here, and I'm here. I stop here. Then minus W, to follow minus W, I have to follow it from the point that I'm at. And minus W is over here. So but the nice thing about vectors is you can move them to go where you want them to. As long as you don't change the direction, you can translate them all over until they're right where you want them to be. So if you're going to treat this as like a force, and you're pushing this block here, then you got to push the block up to here. Now the block is here, and that's what V did. Now I have to impose a negative W from here. So I'm going to follow this direction. I'm going to push, 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 and the block ends up stopping there. So that means that this vector right here is V, but take away W as far as forces are concerned. And that's really the way you have to think about it. You can't just like go jump back down to here, because if you think of forces, the block has been pushed up to here. I think you just have to convince your brain that that's how vectors work. I don't know if that helps or not.
Yes, sir. It makes sense. Thank you.
So this length is length of W, this length is length of V, and this length is the length of this subtraction of the two. So I have the law of cosine all sorts set up. And so now I use the fact that dot product, previous slide, that the dot product of the vector with itself is its length. So this left-hand side is V minus W dotted with V minus W. So again, length squared is a dot product. So those two things are the same. On this side, it's a little bit easier. I just write down the formula I just had. The length of V is V dot V. So that's that one. The next one is just W dot W. And the last one I'm not actually going to change. It's going to be 2 length of V, length of W times the cosine of the angle. So all I did there was take the law of cosines and replace all the lengths with their corresponding dot products, except for these last two. Now, what are we doing here? Well, this one I can use the distributive property on dot products. I didn't tell you that you can do it, but it turns out the distributive property still does work. So I can do V dot V and V dot W, and this minus sign can be actually pulled out as well. So lots of nice things about this work just like a distributive property for regular products. So V dot V, V dot W, but it's minus, so I put a minus here. The next one I distribute the W. And I'm going to be a little bit sneaky, is that if I do distribute W on V, well, V and W can be dot product in either order, so I get another copy of V dot W. I've written it in reverse order. And then the last one, W and W, I've got a minus and another minus, so that would be plus WW. So it's a lot of dot products come out of this length here. I'm just going to recopy the right-hand side. V, W, W, and then minus 2, V, W, and now this is the nice part. Look, I've got V dot V and V dot V on both sides. So I'm just going to cancel them. W, W, I can cancel those because they're the same thing on the other side. So what am I left with here is I'm just left with 2 copies. So I guess minus 2 V dot W. So that's V dot W, that's V dot W. They're both subtracted, so I get minus 2 copies of that. So if I was to solve for cosine here, and this is the point as well, what I wanted to do, is I can just divide over by all of this stuff. So if I divide by minus 2 on both sides, those will end up getting canceled out. So the only thing that's left is this, V dot W on the top and 2 other numbers on the bottom that tie together. And so this is the next property of dot products, is it's not only related to like lengths and angles, it's related to actually the cosine of the angle between. So that's another like use that property. And you can see again, if these are perpendicular, then what's the angle? Well, the angle would be 90. Well, what's the cosine of 90? It's 0. So this side would be 0, which means that this numerator would be 0. And that's just a nice verification that perpendicular comes when the dot product is 0. Let's put that one in your head. So back to the example, maybe we'll do them in 3D. So I could do D equals, we'll just do 1, 2, 3. That's kind of an easy one. We can do W equals minus 1, 1, 1. W, I ran out of letters already. I don't want to use that. So we'll just call it B2. How about that? So I can do this one as 3, 3, okay. Maybe I'll just go ahead and call that V1. So V1 is 1, 2, 3. W is this one. V2 is that. So let's just compute some of the angles. So for V1 and W, I'm not going to try and draw the picture because it starts to get a little hard to see what's going on. But the angle between them, well, the cosine of the angle will be V1 dot W over the length of the 1 times W, length of W. Now we're starting to put a lot more things together. V1 dot W will be 1 times minus 1. So I multiply the first two. And then I add on, multiply the second two, 2 and 1. And then I add on the multiplication of the third one. And that'll be the top. The length of V1 will be the square root of each of these guys squared. So 1 squared, 2 squared, 3 squared. And the same thing for W. Negative 1 squared, 1 squared, 1 squared. If I do this correctly, then the top would be minus 1 plus 2 plus 3, 4. The bottom is 1 plus 4 plus 9, so that's the square root of 14. And then this one is the square root of 3. Make sure you square out all the negatives correctly. So I get that the cosine of the angle is that, so the angle will be arc cosine or inverse cosine of 4 over the square root of 14 times the square root of 3. You can just plug that in your calculator and see what that is. Or just leave it like that. I don't know. It's something, some angle. It's not one you probably know off the top of your head. And then try between V1 and V2. So this one was for V and W. So for V1 and V2, the angle there, so the cosine of the angle for V1 and V2, same formula, V1 dot V2, and then the two lengths go on the bottom. I already know the length of V1, so maybe I can just stick that in square root of 14. What's the length of V2? So the length of V2 will be 3 squared plus 3 squared plus 3 squared. So that's 9 plus 9 plus 9, so that's 27. So that's square root of 27. The length of V2. And now what's the dot product between these? It will be 1 times 3 plus 2 times 3 plus 3 times minus 3. And what does that turn out to be? Well, it's be 3 plus 6, so that's 9, but minus 9. So this whole thing turns out to be 0 over something which is just 0. So, okay, now it still holds from before. The cosine is 0 exactly when the dot product is 0, as we can see this, which means that V1 is perpendicular to V2. And that's a lot harder to see if you were to plot it. But if you did, you would see that if you plot V1 and you plot V2 in space, they would be meeting somehow out there at a 90 degree angle. So for 2 dimensions, it's not hard. You just draw the 2 and you're like, oh yeah, that looks like 90. But for 3 dimensions, or actually even higher, You can talk about perpendicular vectors in whatever dimension you want. And it all comes down to, is the dot product equal to 0? And if it is, boom, that's good. So that's now maybe one last thing before we do our first break here that is nice is sometimes you're going to want to take two vectors, and I'll just draw a picture here. And this is what I'm going to do. Let's call this one. I'm using the letters. Maybe I shouldn't use. I'll make it look like the book. They like to use U as a unit vector, and then sometimes they don't. So it's a little confusing. But the example here is suppose. What's that?
Did you write the book, sir?
Hartman wrote most of it, so I'm going to blame him. I think he made it look like all the other calc books. So U and V, I don't know. Somehow, yeah. I'm going to blame Hartman. I'll just leave it at that. So here's the deal. Suppose you're pushing your lawnmower, along, and so this is a terrible lawnmower, but big person here, and you're pushing the lawnmower, and you want the lawnmower to go this way, but actually, if you look at the forces that are going on it, you probably are pushing more sort of this direction down this. It's really hard to like just push your lawnmower straight without it like tipping up or something. So you're imposing a force sort of down that way. And if you push down at say 150 pounds of force here, or not all of that will be imposed in the direction you want it to go. So you're losing some energy in here because you're basically decomposing it as some of the force is pushing in the direction you want, but really you're losing this force where you're pushing down, probably to sort of maintain contact with the ground. So the catch is how do you decompose the force you're actually doing into the direction that you're moving, and then the direction like perpendicular to that, which is lost. So it's the same sort of thing here. Suppose that you want to go in the direction of U, and you are imposing a force this way. But how much of that force is going along U, and how much of that force is going away from you? So what you want to do is take this and decompose it into two parts. One part of V that is going along U. This is good because I wanted to do this. And then you have a part here which is being lost, which is going away from it. So this guy right here is called a shadow. And you can see he's showing a light bulb. This would be the shadow vector down here. And of course, they don't use the word shadow because that would make sense. But think about like holding your finger up and you're making a rabbit, right? And so this looks like a projector. We've got a projector that's doing that. So this vector down here is called the projection of V onto U. So if you've shown a light perpendicular above V down here, so yeah, it does move here. The shadow vector is not going to be all of V because you've lost some stuff here, but you have a vector that's going along here. So what we want to do is figure out what this projection vector is based on what V is. And there's some formulas, and you can sort of remember all of this sort of stuff. But the projection vector, and we write it like this. This is called the projection of V, and we write a little subscript U to say, this down here. The way to remember it is like down onto U. So you're projecting the vector V down onto the vector V to get this vector here. Well, every vector has two parts. It has a length, and so we want to figure out what that length is. And it has a direction to it. And the direction using sines and cosines, or using the unit vector, is the direction is going to be a unit vector that points along U. So it has length 1. So this was one we have already done. is the direction in the direction of u is I take the unit vector, well, it's not quite a unit vector yet, unfortunately, divided by its length, and it will become, anytime you divide by a length, it becomes a true unit vector. So we get part of our formula. Now, what's the length of this vector here? Well, this length is the length of v because that is the vector v. So if I wanted to figure out the length of the bottom, turns out if I knew the angle here, then what is the length of the bottom part? Well, you just go back to a basic triangle and you realize, let's see, this guy is cosine of the angle. So if I took the cosine, I would get the length of the bottom divided by v, which means that if I wanted to just get this length here, it's the cosine of the angle times whatever the length of the hypotenuse. This is basic trigonometry. This length is the length of v times the cosine of the angle. And boom, you get your formula for the projection vector. And it's got a lot of pieces to it here. You've got u, which is a vector. You've got a length, which is a number. You've got this, which is a number. And then you have to figure out what the cosine of the angle is. So, rewrite that on the next slide so it's not so cluttered. The projection of v down onto u is the length of v times the cosine of the angle. That's a number, so all that's just a number. And then we have a vector, and it's divided by a number. So my favorite stuff, no numbers yet, just all symbols. But if I try and combine that with the thing that I just did, the cosine formula is u dot v over the length of u times the length of v. Then I can condense all this down so there's only u's and v's in the formula. And we plug that right in there. So there. And if I do that, let's see all the pieces that I got here. So I'm going to just do this. I'm going to put u here. That's the only part that's a vector. All this stuff is numbers. So let's see if I can combine this here. So I'm going to get a number times a vector here. So I'll have the length of v right there. But look in the cosine formula. It's got a length of v in the denominator. So that part right there and that part right there are just going to cancel out. So that's good. What else do I have? I've got this u dot v. That's there. And what else am I missing? I got this length of u, but I also have another length of u. And they're both in the denominator. So I will get the length of u. That's the formula that's in the book. It's like a mystery of where it comes from. But if you just draw the triangle and use basic trigonometry, this is not hard to see. This is where it starts to get a little bit of a mystery in there. But that's it. So if you understand that formula, then you can use that formula. So let's do one example of that, and then we'll take a quick break here. So for example, I'm going to go ahead and use V and W just because again I don't like that. So the vectors, I don't remember, we had 1, 2, 3, so that was one of them. And W was 1 minus 1, 1. We'll just do that. So if I took and I wanted to figure out what is the shadow vector if I took and drew W and then I drew V and I shone a light down onto V, what would the shadow look like down onto W? Well, according to my formula, this needs to be the dot product of V and W divided by the length of W squared, and then I just take that and I multiply it by the vector W. So it's a scalar multiple of this second vector here. So V dot W, so that'll be 1 times 1 2 times minus 1, and 3 times 1. If I did that correctly, that should be 2. So 1 and 3, and then the middle one is negative, so I get 2. The length of W is 1 squared, negative 1 squared, which is also 1 squared, so the length of W is square root of 3. So 1 and 1 and 1. Okay. But I square it, so I will get 2/3. And then I multiply that by my vector 1, 1, 1, which I could either write by just doing this, right? 2/3 times 1, 1, 1, or I can put it inside. So minus 2/3, 2/3, and 2/3, like that. So again, and I don't have the directions of these things quite right. If I did W and I did V, so this is 1, 1, 1. But if I took the shadow, and then you guys can make it a little bit longer, so I can get that right. Maybe not there. But if I took the shadow down here, then that vector right there would be, sorry, this should, I put the minus in the wrong place. Sorry about that. Minus is in the middle. So this would be the vector 2/3. Put the minuses in all the right places. Minus 2/3, 2/3. So it's 2/3 of the length of the whole thing would be the shadow. And again, this would be the vector 1, 2, 3. Maybe just for completion's sake, what would this vector be here? So I know that if I go over this amount, I get this bottom vector. But if I wanted to come back up to here, then when I add these two things together, I have to get 1, 2, 3. So without doing any subtractions, like what do I need to do to 2/3 to get it up to 1/3 or to 1? Or to give it away. So I'd have to add on 1/3. So if I went 2/3 and 1/3 for the X direction, I would get 1. For the J direction, or Y, I'm already at minus 2/3. So what do I need to do to add up to that? I need to add on 8/3. So minus 2/3 and 8/3 will give me 6/3, which is 2, which is exactly what I need to do. And then the last one, 3 is equal to 9/3. So I've already got a 2/3. When I add on this, I add this second component, and I get 7/3. So if you knew this vector and you knew this vector, you put the third one by just either subtracting or figure out what I need to add. So that's quite a lot, but there's the three key things, which is, if I had W dot D equaling 0, that means they're perpendicular. Figuring out what the cosine formula is and figuring out what the projection formula is. Those are the three main things that come out of the dot product. Talk about the cross product. We'll do a lot of examples, and then let you guys work on homework. So we'll take a quick break here and come back at say 8:20 or so, and we'll start again. So a little bit. Not cold, huh? Okay, so we'll see you in a little bit.